Welcome back to our discussions of forces in engineering mechanics. In this lecture, we'll learn about the conditions of equilibrium of structural systems. To understand equilibrium of structures, we should start with the laws derived by Sir Isaac Newton. Newton's first law says that if the resultant force acting on an object is zero, the object will remain at rest if it's originally at rest, or in a uniform motion on a straight line. Since we are interested in keeping structures at rest, that is, we do not want them to move, we need the resultant of all forces acting on a structure to equal zero. Newton's second law says that if the resultant force acting on an object is not zero, an object will have an acceleration proportional to the applied force and in the direction of the force. Newton's third law says that the forces of action and reaction between bodies in contact have the same magnitude, the same line of action, and the opposite direction. For example, take a wall. Apply an external force on this wall. From Newton's third law, it follows that the wall will react with an internal force equal in magnitude and opposite in direction to the external force applied. Otherwise, the resultant of forces acting on the wall will be different from zero, and from Newton's first law, it follows that the wall will then start moving. Let's consider a system of external forces and moments acting on a body. In this case, a potato, and I'm doing this to remind you to eat healthily. The external forces can be substituted by the resultant force, which can be found, for example, graphically using the heads to tail rule that we discussed in the last lecture. The same can be done with the external moments. Now we substitute the systems of external forces and moments with their resultants. Note that by doing this, we do not change the external effect of the forces and moments of the body. Under the actions of the resultant force and moment, the body will move and rotate. To prevent the body from movement and rotation, we must hold it in place. Supports are used for this purpose in structural engineering. The body will not move or rotate after appropriate supports are applied. We can say that this body is in balance, or in equilibrium. According to Newton's first law, the sums of all forces and moments acting on this body should equal zero. Here you can see the equations for the sums of moments and forces. The sums of external forces and moments are different from zero. To obtain zero sums, the actions of the supports can be represented in these equations by the resultants of the reaction forces QF and moments QM as follows. In the equations of the sums of forces and moments, we can substitute the external forces and moments with the resultants RF and RM for force and moment. Now substitute the supports with the resultants of the reaction forces QF and QM for force and moment again. Solving the obtained equations leads to the following equalities describing the conditions of equilibrium. These conditions basically describe Newton's third law, stating that the resultants of reaction forces and moments are respectively equal and opposite to the resultants of the external forces and moments. Let's discuss equilibrium in a few cases. We will only consider planar cases for simplicity reasons. In the case shown on this slide, a body is subjected to systems of external forces and moments. We nail the body to the plane and substitute the systems of external forces and moments with the corresponding resultants. The nail will prevent horizontal and vertical movement of this body, which means it will develop a reaction force equal and opposite to the resultant of external forces. As a result, RF and QF balance each other. The nail, though, does not prevent rotation of this body, which means that this support cannot apply a reaction moment. So this support provides translational equilibrium but does not provide rotational equilibrium. This kind of support is represented using the following sign and is called a pin support. Let's consider a book lying on a table. Since the book is not moving, it is in equilibrium. The book applies its weight to the table, and the table reacts with a reaction force equal to the weight of the book. As we discussed, forces can move and rotate objects, while supports are required to prevent movement and rotation. Supports counteract forces by developing reaction forces. To understand how engineers model supports through reaction forces and moments in the analysis of structures, we consider the following bodies subjected to systems of external forces and moments, which are represented here by their resultants, RF and RM. The body is restricted by a system of supports which prevents any movement and rotation. Since the body is not moving or rotating, it is in equilibrium. Now we will imagine that we remove the supports. We've obtained a body with an external force and moment acting on it. As a result, the body will move and rotate. Since we only imagined that we removed the supports, the body should not move or rotate. To keep the body in equilibrium, a force and moment equal and opposite to the external ones should be applied. These forces, QF and moment, QM, represent the resultant reactions applied by the supports. There are several types of supports used in structural analysis. We will only look at planar supports in this series of lectures. The first supports we'll consider are simple supports. These type of supports prevents movement in one or two directions on a plane. Here you can see typical signs representing these supports. Note that the circle at the apex of the triangle represents a hinge, allowing rotation. The support preventing movement in only one direction will be able to move in the perpendicular direction. This support is called a roller or sliding support. It's a bit like a skateboard or a hoverboard, right? You don't go into the ground, but you can move parallel to the ground. Here you can see some examples of roller supports preventing movement in X, Y, or an arbitrary direction. This support develops only one reaction force in the direction in which the moment is prevented. So once again, if you think about it, it is a bit like a skateboard. So when you stand on one, you don't move vertically, but you roll in the horizontal direction. The next support, a non-sliding support or pin support, prevents movement in two independent perpendicular directions. Basically, it prevents any movement on the plane. It is convenient to represent the reaction forces in such a support as acting in two known perpendicular directions, which are usually the horizontal and vertical directions on the plane. A general rule which can help you understand where to apply reaction forces is, if movement is prevented in a certain direction, apply a reaction force in that direction. If a support can move in a certain direction, then there won't be any reaction force developing in that direction. Let's consider reactions in a basic structure, a simply supported beam. The left support is non-sliding or pinned, and therefore it develops two reaction forces in the horizontal and vertical directions. The right support is a roller support which can move horizontally. The second type of support we'll discuss is a fixed support. This support prevents both movement and rotation, and as a result it develops two reaction forces in the horizontal and vertical directions and a reaction moment. Let's consider a few more examples of basic structures. This is a cantilever beam. It has a fixed support at one end. Therefore, it has two reaction forces and a reaction moment. This is a column. It has a fixed support at the bottom and a roller support at the top. Therefore, it develops two reaction forces and a reaction moment at the bottom and a horizontal reaction force at the top end. Altogether, it has four reactions. Now, let's consider how a body can move on a plane. It can move horizontally. It can move vertically. It can rotate. And to keep the body in equilibrium, we need to prevent two independent movements and one rotation. These two movements and rotation are prevented by the reaction forces and moments applied by the supports. These reactions should satisfy the following equilibrium conditions. The sum of external forces and reactions in the horizontal direction should be zero. The sum of external forces and reactions in the vertical direction should be zero. And the sum of moments should also be zero. Note that the horizontal and vertical components of the resultant of the external forces and the resultant of the reaction force are used in the translational equilibrium conditions. The three equilibrium conditions can be combined into a system of three independent equilibrium equations. The sum of all forces in the horizontal direction should be zero, the sum of all forces in the vertical direction should be zero, and the sum of all moments should also be zero. Note that in a three-dimensional case, there are three independent movements and three independent rotations, which will result in six independent equilibrium equations. We will finish this lecture by considering two different types of loads used in structural analysis. The first type of load is a concentrated load, or in short, CL. This load is basically a force acting at a point. It's represented by an arrow. The unit of the concentrated force is newtons or kilonewtons, whatever system you're working in, but units of force. Let's consider a fire engine on a bridge. Here the bridge is modelled as a simply supported beam. The fire engine applies its weight on the bridge through the wheels. Therefore, we can represent its weight by two concentrated loads, F1 and F2, applied at the locations of the wheels. The bridge will react to these concentrated loads by developing reactions at the supports. There is a horizontal and a vertical reaction at the left support, or pin support, and a vertical reaction at the right roller or sliding support. The reactions are also concentrated loads. Another load type is a distributed load, or in short, DL. This load usually represents the weight of a large number of objects or a continuous object lying on a certain area. The unit of distributed loads is Newton per metre or kilonewton per metre, or any other load per distance. Let's consider a beam carrying a heap of rubbish distributed over a certain length. As you can see, this heap is non-uniform and therefore it applies different loads at different locations along the beam. We can schematically represent a non-uniform distribution of weight by a curve, where the vertical distance from the beam to the curve represents the amount of load applied at that point. The external action of this distributed load on the beam can be represented by the total weight of the load applied at the centre of gravity. The total weight of the load can be represented by a resultant force, and now the reaction forces can be found using equilibrium equations. A special case of distributed loads is a uniformly distributed load, or in short, UDL. This type of load is very common in structural design. Let's consider a beam carrying a bath. The bath distributes its weight uniformly over a certain length of the beam. Since the load is uniform, it can be represented by a rectangular distribution. The centre of gravity of this load coincides with the centre of the UDL area. The resultant of the UDL is applied at its centre. And now the reaction forces can be found using equilibrium equations. So we've gone over quite a lot today. We've discussed equilibrium. We then went on to discuss reaction forces that develop in different kinds of supports, because we don't want our potato to move or anything. We've then looked at different types of loads. And all of these are really the basic concepts which will help us design structures. We'll now utilise all that knowledge solving reaction forces in different structures. So please join me for that. Bye for now.